due to economic and operational benefits, electrical energy is generated and distributed in a three-phase form rather than in a single-phase fashion. And this motivates us to study a very special, but from the practical point of view, a very, very important LTI, or a class of LTI circuits, namely balanced three-phase circuits. And we begin our study with the following device. Okay, so consider a 6-terminal AC generator. Okay, so let me roughly draw it. So this is our generator, okay, a device that transforms, let's say, mechanical energy to electrical energy. And from this machine, there are 6 wires coming out, and they are labeled as A prime, B prime, C prime. Okay. Now, this device can be modeled through 3 independent voltage sources as follows. So, one is for the voltage difference between the terminals A and A prime. Okay, and we have VA prime T equals some sinusoidal signal with some magnitude, which we call the source voltage magnitude, and cosine omega t, omega being the frequency of operation. Okay, and then similarly we have another independent voltage source representing the voltage drop between terminals BB prime, and likewise for CC prime. So for the sake of completeness, let me also draw them. Okay, B prime, and here we also have C prime. Okay, now the voltage between the terminals B and B prime is such that it has the same magnitude, it has the same frequency, but a phase difference of 120 degrees. Okay, counterclockwise with respect to the terminals AA prime. So we have therefore Vs cosine omega t minus 120 degrees, and for the VCC prime t we have Vs cosine omega t. So from A to B you go 120 degrees counterclockwise. From B to C you go further 120 degrees counterclockwise. So that makes cosine omega t minus 240 degrees. Okay, which is clearly equal to Vs cosine omega t plus 120 degrees. Okay, so these are all sinusoidal signals. So let's represent them, or let's talk about their phasor representations. Okay, so let's quickly obtain a phasor diagram. Okay, so here we have the phasor of voltage VAA prime. Okay, and then the phasor for the VBB prime, it has the same magnitude, but the phase is 120 degrees shifted in counterclockwise direction. So from VAA prime, what we do is we take this vector and shift it 120 degrees. So that's something like this. Okay, so this is our VBB prime, the phasor of this voltage. And finally, from VBB prime, we go another 120 degrees. Clockwise, we go another 120 degrees clockwise, and we reach VCC prime. Okay. Again, this vector has the same magnitude with VAA prime and VBB prime. So we have VCC prime, and the angle separation is uniform. From here to here, we have 120 degrees, and here we have another 120 degrees, and finally, this angle is also 120 degrees. Okay, so when represented through their phasors, the symmetry is clearly seen, and so that triple makes a balanced set. Namely, they have the equal magnitudes, and the separation is 120 degrees between each. Therefore, their sum clearly will produce 0. Okay, therefore, this VAA prime plus VBB prime plus VCC prime produces 0. Okay. So when we have such a triple, we call that a balanced set. Okay, we're talking about phasors. That is, magnitudes are same, and the angle separation is uniform, 120 degrees between any pair. Okay, so this is called a balanced set. Okay, VA prime, VB prime, and VCC prime. Okay, now this 6-terminal device can be reduced into a 4-terminal one by connecting the primed terminals into a single node. So let's do that. Okay, so Y connection. Now the 6-terminal generator can be connected as follows. This is the triple that represents our generator. Okay, A prime, and B prime, and C prime. Okay, so what we do is we go ahead and connect the primed terminals at a single node. Okay, and we call that node the neutral node, or the neutral terminal. Okay, this is N for neutral, and as for the remaining terminals, we keep their names. Okay, this is A. Here we have B, and here we have C. Okay. Now, usually this connection is drawn in a simpler or more symmetric looking way. And when we do that, we're going to see why this connection is called Y connection. Okay. Now this connection is usually drawn as the following picture. Okay. So here, this node where one terminal of every source meets is our neutral node or neutral terminal. Okay, so this is Rn, and then this is, let's say, A, B, and here we have C. Okay, and then these are connected to the transmission lines. Okay, A, B, and C. Now this is how we represent, when we draw our circuits, a six-terminal AC generator. Okay, so this is called a three-phase Y-connected source or generator. Okay, now in this connection, the voltage between, so these are called now lines because those terminals are now touching the transmission lines. This voltage drop between two lines are called the line-to-line voltage, or sometimes simply the line voltage. Okay, for instance, this is VBC in phasor domain. So this is called line-to-line voltage. Okay, or simply line voltage. Okay, and we have another voltage. It's from line to the neutral node voltage. Okay, and that's denoted by for instance, since this is node A and this is node N, this is denoted by V sub AN. Okay, and this is called line to neutral voltage. Line to neutral. Okay, or sometimes the phase voltage for the source, for the generator. Okay, now let's figure out the relation between the phase voltages, okay, VAN, VBN, VCN, and the line-to-line voltages, okay, VAB, VBC, and VCA. So, when the generator is balanced, by which we mean that the voltages here, VAN, VBN, VCN, they all have equal magnitudes, and the phase separation is 120 degrees. Okay, from VAN to VBN, you go 120 degrees clockwise. From VBN to VCN, you go another 120 degrees clockwise. Okay, so we have, or we can write, therefore, VAN equals some magnitude, let's call it source voltage magnitude, and without loss of generality, we can take VAN to be reference. Okay, so we're taking its phase to be 0. And then VBN has the same magnitude, and we go clockwise 120 degrees, so that produces minus 120 degrees. And for VCN we have the same magnitude, and we go further 120 degrees clockwise, so that makes minus 240, but minus 240 is same as plus 120, so let's write here 120 degrees. Okay, now these are the voltages, our balanced set, and from these phase voltages or line to neutral voltages, now let's try to obtain the triple that's associated to line-to-line voltages. Namely, let's obtain VAB, okay, the voltage drop here, VBC, the voltage drop here, and also VCA, the voltage drop between the top and bottom lines or the wires. Okay, so what's VAB? VAB is, by definition, VAN minus VBN. Okay, so that equals VAN minus VBN. So the phase voltage for phase A and the phase voltage for phase B. Now this difference is the line-to-line voltage between the lines A and B. Now that equals what? Vs, no phase, minus the same magnitude, 120 degrees. Since we're doing subtraction, let's write things in rectangular coordinates. This we can write as Vs minus Vs times cosine minus 120 degrees plus J times sine minus 120 degrees. Now cosine minus 120 degrees is minus 1/2, and sine of minus 120 degrees is minus square root of 3 over 2. So here we have square root of 3 over 2. Okay, and now let's perform this subtraction. So that produces 1 minus minus 1/2, so that makes 3 over 2. And here, this is purely real, and the imaginary part of this difference will simply be the imaginary part of the second piece. Hence, we have Vs 3 over 2 plus J square root of 3 over 2. Okay? And this can be written as square root of 3 times Vs times 1/2 plus J, excuse me, square root of 3 over 2 plus J 1/2. Okay. Now this, if you write it in this form, this square root of 3 over 2 is cosine of 30 degrees, and this 1/2 is sine of 30 degrees, the same angle. Therefore, we can easily transform this back to the polar coordinates, and what we have here is the following: square root of 3 times the magnitude of the phase voltage, okay, with phase 30 degrees, okay, because this is cosine 30 and that's sine 30. So, similarly, we can figure out VBC and VCA. Let's do them also. VBC. So that's the line-to-line voltage between the lines B and C, or between the nodes B and C. Again, by definition, that's VBN. Okay, the phase voltage for the phase B or the source B minus VCN, and that's with phase minus 120 degrees minus with phase plus 120 degrees or minus 240. Let's write it as minus 240 degrees. Okay. Now this difference can be written as this scalar minus 120 degrees. Okay, magnitude 1 and phase minus 120 degrees times Vs phase 0 minus magnitude of Vs phase minus 120 degrees. Okay. Now, once it's written in this form, we can easily use our previous computation to write or to replace that term. Okay. Note that this is, forget about this, this is no other than VAB. Okay, because VAB is given as this subtraction. Therefore, we know what this is already, square root of 3 times source voltage magnitude with phase 30 degrees. And then we're now multiplying this by this complex number whose magnitude is 1 and phase is minus 120 degrees. Therefore, all this will do is it will affect the phase. To 30 we add minus 120 degrees, therefore it produces minus 90 degrees as phase. Okay, so VBC therefore has the same magnitude and its phase is minus 90 degrees. Okay, so that equals square root of 3 Vs and the phase is minus 90 degrees. And likewise, VCA can be computed to equal this thing, and then you take the phase and rotate it 100 or add or go 120 degrees further in clockwise direction. Okay, so VCA is VCN minus VAN, and that equals square root of 3 times the magnitude of phase voltage of our generator. And from this you subtract 120, so that makes minus 210, which is same as plus 150 degrees. Okay, so we have obtained therefore our triple, the line-to-line voltages, or simply line voltages. We have VAB, we have VBC, and VC, and we have VCA. Okay, and now we can compare them with the triple of phase voltages, namely VAN, VBN, VCN. As for the magnitudes, the line-to-line voltage magnitudes, for each line-to-line voltage, it's the same, and it's square root of 3 times line-to-neutral voltage, okay, for the Y connection. And as for the phases, those are what we have obtained, 30 degrees, minus 90 degrees, and 150 degrees. So we observe therefore that line-to-line voltages inherit that balancedness property of line-to-neutral voltages. Namely, they have the equal magnitudes, and also the separation, phase separation, is uniform. From VAB to VBC you go 120 degrees clockwise, from VBC to VCA you go further 120 degrees clockwise. Now, to see everything in a clearer picture, let's place all these voltages or these two triples on the same phasor diagram. Okay, so this is our VAB. Okay, this is the phasor diagram. So we have this balanced triple of phase voltages, VAN, VBN, we go 120 degrees, therefore this angle here is 30 degrees, and then we go 120 degrees clockwise further, and that produces VCN. Okay, so this is also 30 degrees here. So that's our phase voltage triple. VAN, VBN, VCN, they all have the same magnitude, which we denote by this VS here. And the separation is from VAN to VBN, 120 degrees, and then from VBN to VCN, you go another 120 degrees clockwise. Therefore, this angle here is also 120 degrees. Now, from this triple, what we have obtained is, we obtained the line-to-line voltages. VAB, by definition, is VAN minus VBN, or VAN plus minus VBN, which would be this this vector here, okay? And then this is 30, this is also 30, therefore that makes this angle 60 degrees. So we have two vectors of equal magnitudes, and the separation is between them is 60 degrees. So that produces this vector, which is of equal distance to both of its components, minus VBN and VAN. Since this was 60 degrees, these angles should be 30, 30. Therefore, this is 30 degrees, okay? As expected. And then, as for the magnitude, it's square root of 3 times the magnitude of either of its components, okay? Because the components have the same magnitude. So this is our VAB. Now, this is VAB. From VAB to VBC, what we do is we go 120 degrees clockwise. So this is 30 degrees, and you go 120 degrees, so that makes negative vertical axis, okay? So this is our, therefore, VBC, where the phase is clearly 90 degrees, okay, or minus 90 degrees, as expected. And finally, from VBC to VCA, you go another 120 degrees, so that produces this vector here, VCA, and this separation is also 30 degrees, okay? So, once again, the line-to-line voltages, they inherit the balancedness of the line-to-neutral voltages, okay? The angle of separation is 120 degrees between them, and they all have the same magnitude. As for the ratio of the magnitudes of line voltages to phase voltages, the ratio is square root of 3. Okay, the line-to-line voltages for Y connection is square root of 3 times the phase voltage, or the line-to-neutral voltage. Okay. Now, if a Y-connected source or Y-connected generator is connected to a Y-connected load, then the resulting circuit is called a Y-to-Y connection, or Y-to-Y topology. Okay. So let me quickly draw how such a circuit can be represented. Okay. So we now talk about Y-to-Y circuit, and we will always be talking about the balanced case. We're going to give the precise definition of balancedness soon. So here we have our Y-connected source or generator, okay, with nodes labeled as A, B, and C. Okay. polarity here. Plus minus, and plus minus. This voltage here is VAN, so we are in phasor domain. This voltage here is VBN, and this voltage here is VCN. Okay, and this node or terminal is our neutral node. Okay, and then here we have the Y connected load. Okay, and usually the convention is such that nodes at the load side are represented by capital letters. Okay, so here we had ABC lowercase, there we have ABC capital. So let this be B, this is A, and this is C. Okay, and once again the convention is such that B is connected to B, A is connected to A, and C is connected to C naturally. Okay, so let's do that. And how we connect them is by the so-called transmission lines. And then we connect A to A. Okay. Now, this is the source, that's the load, and these are the transmission lines connecting the respective nodes. Since geographically speaking, these distances between generator and the load, or the producer and the customer, is large, we cannot ignore the impedances of the transmission lines. Therefore, transmission lines represented by some non-zero impedances, which are called Z lowercase l, Z lowercase l, and Z lowercase l. Okay, now what else? So in this circuit there are three zones, so to speak. Okay. Now this side, or this piece, is called the source side. This side, or this piece, is called the load side. And here in between we have the piece representing the line. Okay, so here we have the source, and as is clear by how it's drawn, it's Y connected. Okay, and here we have load, again Y connected. Okay, and each of these ports are represented by an impedance, and that's each of those impedances are called the per phase load impedances. Okay, so this will be ZA, this is ZB, and this is ZC. Okay, and we'll be always working with the balanced, under the balanced situation, which requires that all these per phase impedances are equal to one another. So therefore we can replace them and write Z sub L. Okay, now let's do some labeling for the voltages and currents. So here, okay, so here we have already labeled the voltages. Those are the source voltages, okay, phase voltages at the source side, and then we have the currents leaving those voltage sources. Okay, this is called IC, this is called IA, and this is called IB. Okay, and then these currents are traveling through the line, and when that's the case, we call them also line currents. And then finally, we have the currents flowing over the per phase loads. Okay, this is called I capital C, this is called I capital B, and this here is I capital A. Now in this Y to Y connection, clearly the per phase currents at the source side equals the per phase current at the load sides. So I capital B therefore equals I lowercase b, and same goes for the other currents. And this voltage here is called line voltage or line-to-line voltage, and this is the line current, and this here is our line. Okay, now sometimes there's also a wire connecting these two nodes or terminals. Okay, and this terminal is also labeled end. Okay, this line or that wire is called the virtual ground. Okay, or sometimes called the neutral line. Okay, now through that circuit, let's now introduce some definitions. Okay, some definitions. We have VAN, VBN, and VCN. The letters are lowercase. So those are the voltages, per phase voltages, at the source side. Okay, so these are phase voltages on the source side. Which is Y connected. Okay, and we have V capital A N, V capital B N, and V capital C N. These are the phase voltages on the load side, which is also Y connected. So we're talking about these voltages, plus minus VAN, plus minus VBN, and plus minus VCN. Okay, so those are the phase voltages on the Y connected load side. Okay, and IA, IB, IC, they are the phase currents. Okay, the currents leaving the independent voltage sources on the source side. Okay, source side, and I capital A, I capital B, I capital C, they are the phase currents on the load side. Okay, and in this Y to Y connection, clearly the phase currents are equal to one another. So I lowercase a equals I capital A, and so on. Okay, and I lowercase l is any of the line currents. Okay, so this is the line current, and V sub L is line-to-line voltage, or in short, line voltage. Now, since the line impedance is non-zero, the line voltage on the load side and the line voltage on the source side are different. Okay, so in this case, what we're denoting is the line voltage on the load side. Okay, so line voltage on the load side. Okay, now by balanced we mean, let's be precise what we mean, okay, because it's a Y-to-Y circuit balance. It means basically symmetry, and the symmetry both from the impedance point of view, okay, and also from the voltages of the source point of view. Okay, so by balancedness we mean, or by a circuit being balanced, we mean that the source voltages, they make a balanced set. That is, they have all this equal magnitude and the phase separation is uniform, 120 degrees between any pair. Okay, and also we mean by balancedness, we mean all the line impedances are equal. That's why we're denoting them by the same notation, Z sub lowercase l. And also balancedness requires that all the per phase impedances ZA, ZB and ZC are equal. Okay, so we're denoting that by Z sub capital L. Okay. Okay, so put that as a remark. Okay, so what we mean by balancedness is the following. First, equal magnitude phase voltages with 120 degrees phase separation between any pair. Okay. 2, we require same line impedance. Okay. Clearly that's a very reasonable assumption to make, because we will use the same wire to connect any two pairs of terminals. And the third condition, which we require in order to be able to call our circuit balanced, is symmetry, or the uniformity of the phase impedances on the load side. Okay, same load impedance, Z sub L. Okay. Now, if these conditions are satisfied, under which we can call the circuit balanced, studying the circuit becomes very simple if you exploit the symmetry, which we will. So let me put that down as a remark. When ZA equals ZB equals ZC, okay, the per phase impedances are the same, which then is called Z sub L. The load is said to be balanced. Okay, and we will always assume this in our studies. Then neutral wire, if exists, carries no current. Okay. Now why that's the case? Now suppose that we have a wire that connects this node to that node. Okay. Due to symmetry of the circuit and due to the balancedness, what we can do is we can consider only one source at a time, killing the remaining two. So that will produce some current, and then do the same thing to other sources. So for each source we will have a component, okay, a current. Due to symmetry, because all the impedances are the same line impedances, same load impedances, and also the magnitudes are the same for the sources. Each of those components, I'm talking about the current passing through that wire, will have the same magnitude. Okay, and since also this phase separation between those voltages, the source voltages, are 120 degrees, that property will be inherited by that current. Okay, those three currents flowing over the neutral wire. And then, since the circuit is linear, we can apply superposition. When these three sources are active simultaneously, the current here will be the sum of those three currents. Now, since those three currents make a balanced set, their sum equals 0. Okay? Therefore, when these three sources are active, there will be 0 current passing through this wire. Now, 0 current through this wire means that the node voltage here and the node voltage here is the same. Okay, there's no voltage drop across these two terminals. Therefore, you can take this either as open circuit or a short circuit. Okay, therefore, in a balanced circuit, even when the neutral line does not exist, the neutral points will have the same potential. Okay, at the load side and the generator side have equal potentials. Okay, so that means, and that's why we're not labeling this as capital N. Okay, because we use capital letters on the load side, but this letter is lowercase, just like here, because this node and that node, they have the same potential. So for all practical purposes, we can consider them to be the same node. In other words, we can take this node and take that node and combine them together and treat them as a single node. If you do that, the circuit all of a sudden becomes separable. Okay, and that separability allows us to consider so-called per-phase circuit, which will simplify our analysis tremendously. Okay, so this separability allows us to work with the so-called per-phase circuit. Okay, per phase. Okay. So, thanks to per phase circuits, we can study each phase separately. And due to symmetry, studying just a single phase will be sufficient. Why is that? Let's see. So this is phase A, let's say. Okay, now this ground node is corresponding to our neutral terminal in the Y-to-Y circuit. This node is A. This is our phase A voltage on the source side, and here we have the transmission line with impedance ZL. This is node capital A, and this is our one of our per phase loads. Okay, ZL. And this voltage here is VAN. Okay. The ground node is the terminal N, or the neutral node in our Y-to-Y circuit. Now, this is a very simple topology, and we can compute anything we want very easily. So this current is the phase current for the Y-to-Y connection, phase current for the source, also the phase current for the load, and also it's the line current. Since there is a single loop, there is a single current, and that current can be labeled by IA. Okay. Now let's figure out, assuming that we know the phase voltage at the source side, let's figure out the line current and also the phase voltage on the load side. Okay, IA equals VAN, this per phase voltage, divided by the effective impedance seen by the source, which is line impedance plus load impedance. ZL plus Z capital L. Okay. And VAN, once IA is computed, VAN can simply be computed by multiplying that current by the impedance, or VAN can be computed through voltage division. And we have IA times ZL. Okay. Now, likewise, we have IB VBN over the same denominator, because we're working with a balanced circuit. All the line impedances and all the load impedances, they are the same. And VBN is IB times ZL. And finally, IC is VCN over the same magnitude. And V capital CN is IC times ZL. Okay, now you've performed the division and obtained something, and that something can be written in polar form as the magnitude, okay, the current magnitude, and it will have some phase. Let's call it theta. Okay, now if you compare this division to division here, they have the same denominator. As for the numerator, those phasors, they have the same magnitude. Therefore, the only difference between this current and that current will be their phases. Okay, so it will have the same magnitude, and the phase will be different. How different? Now, the phase of VBN compared to VAN is such that you go 120 degrees clockwise. Therefore, if the phase of this guy is theta, the phase of IB would be theta minus 120 degrees. And then from VBN to VCN, you go further 120 degrees clockwise. So that means from IB to IC, you go 120 degrees clockwise. And that produces IL theta minus 240 degrees or plus 120 degrees. Okay. Similarly, for the phase voltages, so this will be some magnitude with some phase alpha, and then the remaining two phase voltages will have the same magnitude, and the phase separation will be uniform. VL alpha minus 120 degrees and magnitude VL alpha plus 120 degrees. Therefore, because we're dealing with a balanced circuit, the balancedness of the source voltages VAN, VBN, VCN will be shared by all the triples, be it current or voltage, throughout the circuit. So we will have the same, or the balanced phase currents will have the balanced phase voltages on the load side, and so on. Okay, so let's end this lecture by that simple but important observation. Okay. Note that IA plus IB plus IC, this triple is a balanced triple, therefore their sum equals 0. And likewise, VAN plus VBN plus VCN. So they make a balanced triple, therefore the sum is 0. Okay, and that's all due to the fact that our circuit is a balanced three-phase circuit.